What if the very features that make a drug work better are the same features that make it nearly impossible to characterize? That's the exact paradox sitting at the heart of modern GLP-1 peptide therapeutics, and it's something our analytical teams run into on a regular basis. I'm Raghuveer Singh Parmar and I lead peptide characterization work at Resolve Mass Laboratories, where we specialize in solving some of the most analytical demanding challenges in the peptide drug space. Today we are going to talk about something that doesn't get nearly enough airtime in the scientific discussion: why sequencing GLP-1 peptide is so much harder than people expect, and what it actually takes to get it right. Why GLP-1 peptides are difficult to sequence. So let's start with the why. GLP-1 peptides, drugs like semaglutide and related analogs, are engineered. They are not naturally occurring sequences. Pharmaceutical scientists deliberately introduce non-natural amino acids and lipid chains, attach PG polymers, all to make the molecule more stable, longer acting, and therapeutically effective. And it works. These modifications dramatically improved half-life and pharmacokinetics, but there is a catch. Those same modification makes the molecule a nightmare for my mass spectrometry. The features that protect the drug in the body also protect it from your analytical workflow. So when you try to sequence or confirm the structure, you are essentially fighting against the molecule's own design. Let's break down exactly what you are up against and what's creating the problems. So, non-natural amino acids and chemical modifications. The first major challenge: the non-natural amino acids. Residues like alpha amino isobutyric acid, AIB, and D amino acids simply do not exist in standard protein databases. When your search software doesn't recognize a residue, it either misidentifies it or skip it entirely. That's not a minor inconvenience, that's a gap in your sequence assignment, and in a regulatory context, that gap is unacceptable. And it gets more complex from there. These non-natural residues also produce unpredictable MS-MS fragmentation behavior. You are not getting a clean B and Y ions, you are getting fragmentation patterns you have to interpret almost from first principles. That dramatically increases the manual burden on your analytical scientists. Then layer on top of that the chemical modifications, lipidation and pegylation especially. These are added for good pharmacological reasons, but analytically they introduce heterogeneity. Your chromatographic peaks broaden. Ionization in ESI-MS gets suppressed and your mass spectra become overlapping, complex, and genuinely difficult to deconvolute. At Resolve Mass, we have worked on molecules where a C18 lipid tail was conjugated through a linker to a lysine residue embedded mid-sequence, and getting that localization confirmed required a bespoke digestion strategy followed by hybrid fragmentation methods. It's a kind of challenge that demands experience and not just the instrumentation. Enzymatic digestion and MS-MS fragmentation. Now, the classic approach to peptide sequencing is bottom-up. Digest the protein, run fragments through LC-MS-MS, and piece together the sequence. Straightforward in theory, but with modified GLP-1 peptides, it's not. Your proteases often can't even access the cleavage sites. A bulky PEG chain or fatty acid conjugates physically blocks enzyme access. That's steric hindrance doing what it's designed to do. And when you combine that with non-natural residues disrupting protease recognition, you end up with incomplete digestion, large undigested fragments, and poor sequence coverage. Then in the mass spec, instead of the canonical B and Y ions you rely on for confident sequence assignment, you get internal fragments, neutral losses, and suppressed diagnostic ions. The spectrum looks like noise until you know what you are looking for, and even then, it requires careful manual validation. Here is one that catches even experienced teams off guard: isobaric residues. Leucine and isoleucine have identical nominal masses. Without specialized technique like ETCH, defragmentation, or tandem MS workflows designed to distinguish them, you simply cannot tell which one is in your sequence, and that distinction absolutely matters for the regulatory submissions. And to this, the sheer complexity of high resolution mass spectrometry data sets, thousands of peaks, overlapping signals, modifications that the software has never seen, and you quickly realize that automated data processing alone won't get you there. Expert human curation isn't optional, it's really very much essential. Let's talk about regulatory expectations. So, all of this is happening under significant regulatory scrutiny. Agencies expect full primary structure confirmation, including modification, localization. They want impurity profiling, force segregation studies, validated, reproducible methods that meet ICH standards. So you are not just solving an analytical puzzle, you are solving it in a way that's documented, defensible, and compliant. That's very much a different bar. So, advanced analytical strategies. So, what does the solution actually look like? The short answer is no single technique is sufficient. What works is the multi-technique integrated workflow. You start with intact mass analysis using high resolution mass spectrometry HRMS, ideally coupled with UPLC to get the accurate molecular weight and an initial read on the molecule. Then you move into multi-enzyme digestion, not just trypsin, but a combination of enzymes like gluci, ASPN, and chymotrypsin to maximize sequence coverage from different angles. The fragmentation strategy matters too. At resolved mass, we routinely combine HCD, ETD, and ETHC defragmentation modes. Different ions, different coverage, and critically ETT-based methods are what allows you to distinguish leucine from isoleucine and confirm modification sites with real confidence. Custom bioinformatics is also non-negotiable. Standard database search engines were built from natural proteomics. For GLP-1 analogs, you need custom modifications defined, de novo sequencing algorithm, and in many cases, manual spectral annotation by scientists who understand what they are looking at. And finally, orthogonal conformation. NMR, for example, provides structural information. Mass specs simply cannot. Together, these approaches give you the picture that's complete enough to stand up to a regulatory review. So here is what I want you to take away from this. The complexity of GLP-1 peptide sequencing isn't a temporary problem waiting to be solved by better software. It's inherent to the design of this molecule, And as the industry pushes towards even more complex analogs and multi-modified peptides, that complexity is only going to increase. The teams that will get this right are the ones who invest in integrated workflows, advanced instrumentations, and the scientific expertise to interpret what they are seeing. If you are working on a GLP-1 analog, a long-acting peptide, or any modified therapeutic peptide and running into characterization challenges, we'd genuinely like to hear about it. These are exactly the problems our team at Resolve Mass Laboratories is built to tackle. Drop a comment, reach out to us directly, or let's start a conversation, because in this field the analytical challenge is the scientific challenge, and getting it right matters a lot. Thank you so much for watching this session, and I will see you in the next one. Goodbye for now.